So let's say we are building the most basic URL shortener, which is asked everywhere. So someone gives us a long URL, we generate ABC123. And later when somebody opens slash ABC123, we send them to the original URL. At high level, this is just a map only, right? ABC123 points to some long URL. So the first thought is completely reasonable. Put it in a JSON file, and honestly, for 5 links, it will work like charm. But now, two people create links at the same time. One process reads the file, another process also reads the same file. Both write back, and suddenly one person's link disappears. So the question is not where do we store bytes? The question is what promises do we need from the thing holding your data? That thing is basically the database. Quick expectation before we go deeper. This is not going to be a memorized database name series, and it is not a pure database internals course as well. The goal is much more practical. We will start from the beginning, like what even is a database, then slowly build up to SQL, indexes, caching, SQL versus NoSQL, transactions, replication, sharding, cap theorem, and finally we will design a small URL shortener at the end. So if you are a CS guy or you can code, but databases feel like a black box, this series is for you. In this first video, I am not trying to teach SQL syntax or B trees or ACID properties. Today, we are just answering only one question. Why does an app need a database in the first place? Once that is clear, every later topic has somewhere to attach. I want to be very careful here because a lot of explanations make the file look dumb. This is not dumb. A file is perfectly good place to store data when the rules are very simple. If we have three records, read the file, parse JSON, find the key. That's it. But think about it properly. Our app does not only store data, it asks questions. Do we already have this short code? Give me the long URL for this code. Show this user's last 10 links and delete expired links. Once those questions become normal, the file itself is not enough. Not because files are bad, because we are asking for behavior around the data. Storage is the easy part. Shared, safe access is the hardest part. So, what breaks first? First finding. If the file has 3 million links and we need one code, are we reading all 3 million entries every time? That is just waste, right? Second, updates. Let's say we want to change a long URL. What if the process crashes halfway through writing the file? Do we have the old data, the new data, or some half written nonsense? Third, concurrency. Two requests come at the same time. Both think the code is free. Both try to write. Who wins? Do we even know? Fourth, rules. We need shortcode to be unique. We need created at. We need user ID to exist. Where are these rules enforced? We can build all these ourselves around the file. But that is the funny part. If we keep adding query logic, update logic, locking, recovery, and rules around a file, we are slowly building a bad database. So, a database gives us more disciplined shape. In a relational database, at high level, data lives in tables, and a table is a named collection of rows. So for our app, we can have a table called shortlinks. Each row is one shortlink, and each row has the same named columns, which is short ID, long URL, user ID, created at, maybe expires at. This sounds very basic, right? But it is doing something important. It is making the shape of the data explicit. Shortcode is text. Created at is a timestamp. User ID points to a user. Now the app and the database can agree on what a valid record looks like. That agreement is the beginning of the contract. Now, what does the database actually give us? First, query. We can ask, give me the row where shortcode equals ABC123. Later, We can ask more interesting questions as well, like show me the last 10 links that user created. Second, update. We can insert a link, change a link, delete a link, and the database has a proper way to do it. Third, rules. We can say short code must be unique. So, if two requests try to claim the same code, the database itself can reject one, not our random app logic in four different files. The database itself. Fourth, concurrency. Multiple users can hit the app at the same time, and the database has mechanisms to decide what happens when reads and writes overlap. Fifth, durability. Durability means if the database says done, we expect that data to survive normal failures, right? Not all failures in the universe, obviously, but normal crash recovery is part of the promise. So the useful decision is this: a database is a storage plus a contract, not just where the data sits. What the system promises about the data. One more thing before we go into SQL in the next video. Database is not one single shape. A relational database organizes data in tables and relationships. A document database stores document shaped data, usually close to how the app reads. A key value store is like, give me the value for this key, which is exactly why caches often feel like key value stores. A graph database cares about relationships as first class things. We don't need to learn all of them today, but this framing matters. Every database is choosing a contract. What shape of the data, what questions are fast, what rules are protected, what failures are handled. If you remember that, you already understand more than the usual definition. So, yeah, at high level, this is a mental model. A file stores bytes, a database stores data with behavior around it. It lets us query, update, enforce rules, handle multiple users, and recover from normal failures. For our URL shortener, the important thing is not the data moved from JSON into a fancy box. The important thing is that the app now has a place it can trust. Database equals storage plus contract. That is the whole thing. Next, we need to learn how to ask this database questions. That is where SQL comes in.